Okay, we are in the physical chemistry 364, going through quantum theory of electrons, and today is our presentations on postulates of quantum mechanics, which are fundamentals, summary of all things that we were doing before. First speaker is Tim Burns. Time limit is 5 minutes. If you speak longer, I will push you from the podium. If you speak shorter, we will, everyone will ask you questions.
All right, so is it fine if I full screen it? It's not
yes, yes. And you can, yeah.
Okay, so I have the first postulate of quantum mechanics. So the first postulate states that the property that the analyzed particle will be found at a specific time. So the first postulate states that the property that the analyzed particle will be found at a specific time and within a spatial interval of the width dx centered at x can be calculated. So pretty much it just means the physical system is completely described by the wave function by xt. Now you can have more inside of pi, so you can have x, y, z, and then all be in three-dimensional space. But just for simplicity, I'm just using x, so like on a line. And then the equation for the probability density is equal to the conjugate of the wave function times the wave function, or that'll just be the wave function's magnitude of the wave function squared times dx. One important thing that we have to do is normalization. So what that does is it sets the probability of the particle being found in a particular interval centered at x to be between 0 and 1. And the main purpose of this is to actually like scale it, so that like if you wanted to like compare any wave functions, if they're on like different scales, you obviously can't compare it. So pretty much what we do is we take this equation, which really the magnitude of that squared times dx is the interval over, we set the interval from like on the timeline of x, I shouldn't say timeline, but on the line x over like all of infinity, that'll be equal to 1 or 100% probability, which makes sense. It has to be somewhere. So there are 3 wave function requirements. So in order to actually compute any of this, the wave function has some things that it has to meet. So the first thing is that the wave function must be a single value in spatial coordinates. Second thing is second derivative must exist. That also applies that the wave function itself has to exist at its first derivative. The wave function also cannot have infinite amplitude over a finite interval. So I'll just go into more depth on these. So like I said, wave function has to be single valued. So over here we have an example where the function isn't single valued. Function is on the y-axis and the x-coordinate is on the x-axis. So in between those gray lines, we have where there's multiple values, like 3 values for x, and that doesn't make any sense because if we're using a multi-valued wave function, then that'll end up giving us multiple values for the probability density. Obviously, you can have multiple probabilities at one point. Second one is the second derivative of the wave function must exist. So like I said, that applies that the wave function and its first derivative are also continuous, because you can't take a derivative of something that's not continuous. So that we must use the second derivative because it's essential for actually using the Schrodinger equation, since it's a second order differential equation. And for requirement 3, we cannot have an infinite amplitude over a finite interval. There I have another figure of that. So once the wave function reaches infinity, it can't be normalized, because if we're using the equation down at the bottom and we have infinity equals 1, well then that means that all the points where the wave function equals infinity, there's 100% probability. And then where there, when it is finite, the wave function is finite, then that means that there's absolutely no chance that it's there, which doesn't make sense once again. And here I have my references.
Okay, Let's thank Tim for a nice presentation. Any questions from here or from online? Just raise your voice if you want to ask from online. If no, questions 1, questions 2, questions 3. So let's thank Tim once again and invite Jared to the podium so that they stay in time. Floor is yours.
All right.
Perfect timing, exactly 5 minutes.
Okay, good.
All right. So I had the second postulate of quantum mechanics, and it states that there is a Hermitian operator corresponding to each observable property of a particle. So what is a Hermitian operator? A Hermitian operator is a linear operator that obeys for all well-behaved functions. So you have to have a nice function that would be continuous and not have any breaks in it or anything. So and then a Hermitian matrix is a complete square matrix that is equal to its own conjugate transpose. And transposing reproduces the same matrix. So it can deal with eigenvalues. So eigenvalues of Hermann operators are always real. And then the eigenvalues are always orthogonal to each other or can be made orthogonal to each other through linear combinations. So at the bottom left of the screen is an example of a Hermitian matrix. And you can notice that the diagonals are all real numbers. That has to be so that you can transpose it to get the same function or matrix again. And then the middle of the screen, I just plugged that matrix into MATLAB and said, find me the eigenvalue of it. And it gave me all real numbers. So you can see that that works. Then on the right side of the screen, I just put in two matrix into MATLAB and had it transpose it. So the bottom one is transpose matrix of the top matrix. So here are some useful equations. And you can see it takes an observable and replaces it with an operator and then puts it into equations like momentum, kinetic energy, potential energy, total energy, and angular momentum. So now what can this be used for? If you kind of go on some derivation of it, if you let a hat be an operator and f of x be a function on which a hat can act, if a hat operating on f of x returns the same function for f of x multiplied by a constant, then f of x is an eigenfunction of a hat with eigenvalue k. And you can see that in the first equation. And then for the second equation, if you let a hat be an operator and phi and psi represent two arbitrary well-behaved functions, if the relation is satisfied where dt is over all space, then a hat is a Hermitian operator. So then what can we do with this? Hermitian operators can be used to solve complex quantum mechanics problems that use complex numbers, and it helps them kind of relate back to real numbers. And one example I found, which I found pretty neat, there was a paper on which some scientists looked at the electron energy of a cyan dye. So it would be the middle carbon-carbon double bond, and then they used a one-dimensional particle in a box equation and derived it and used Hermann operators to end up getting the 3D model of it equation. And then their results that they used just calculating it on paper were very similar to it when they actually tested it in a lab. So summary, Hermann operators serve as a link between observables and operators and can be used in quantum mechanics equations. And here's a list of my sources.
Okay, please join in thanking Jared. Anything was unclear or you want to learn more from him? Anyone has questions on online? Questions 1, questions 2, questions 3. Let's thank Jared once again.
Awesome. So this is we're going to go over the third postulate of quantum mechanics, and this is basically where like the word quantum comes from quantum mechanics. So what exactly is the third postulate, you might ask? And the third postulate says that for every observable operator in quantum mechanics, for every observable in quantum mechanics, it is represented by an operator. So like, for example, the observable positive A or X hat would be our operator. It got rid of the picture that I was supposed to have here, so sorry, team. So moving on, what is an operator? An operator is like an instruction, a symbol, or letter that tells us to perform a more mathematical acts on a function. Basically, they act on a function, however, normal function rules apply. So why is this a postulate? This is a postulate because it allows for the reproduction of these measurements. So if we can't reproduce the results, how can we confirm our findings? From the University of Manchester in the UK, it says, if the particle was not initially in the state of a result of a measurement, was not predictable in advance, but for the result of the measurement to be meaningful, the result must be of subsequent measurement must be predictable. So this, we go on to show how operators can work together in functions. So if you have, and this is for positive and negative. And so so we have Q1 hat plus or minus 2Q hat all multiplied by f of x is equal to Q hat f of x plus or minus Q hat f of x. So these are our operators, and we can see how normal function rules apply here. Again here, so if you have Q3 hat, it would be Q1 times Q2 hat. And that's the end of my presentation.
Okay, thank you, Spencer. Okay, thank you. Nice seeing you. So you're less formal than previously.
A bit less, yeah.
Oh, and you have musical instruments on the background.
Oh, yeah.
So, sharing screen. Everyone sees Adam well in the class? Okay, floor is yours. We are ready to listen.
Okay, well, I chose postulate 4, and it's got some pretty interesting utility when you're making measurements on particles and such. So first, before we can, I guess, use the postulate, we need our wave function to satisfy a normalization condition, which is given by equation 1. Yeah, it's important to note that our wave function has a complex value, so we can't really make any determinations of magnitude and direction that aren't relative without special operators like A, we'll call them, and their eigenvalues that can be corresponding to real numbers that come from, I guess, real measurements. And so if we have an observable A, or I guess an observable alpha, can attach its operator by a caret. It has eigenvalues AI and eigenfunctions associated with it. If we take a lot of measurements on our wave function, we can establish a mean for our eigenvalues within the function using equation 2 here. Basically, it's just this will give us the average value for A, and this can actually be used to determine the position of the particle, just as long as our function satisfies the normalization condition. I have a side note there. It's basically saying that psi star is a conjugate. Basically, it just removes the imaginary component of the wave function. This is kind of necessary when we're making real real determinations from our measurements, because we want a real result. We don't want there to be an imaginary component to our real result. Yeah, this is taken over all of space, and that's what negative infinity to infinity on the integral means, as well as the dt there. That's it.
Okay, check if there are any questions in the class. Any questions online? I do have one brief question. Can you please swap one slide back? So it is an extra question with a star, but would you be able to draw a strategic plan how to derive this equation out of the time independent Schrodinger equation?
I'm not sure I understand.
Your operator A, if we replace A with operator of total energy, do you think it is possible to not to postulate this equation but derive it?
Yeah, probably.
What would be your plan? How will you derive it? And anyone in the class online or in face-to-face is welcome to. So if we replace A caret with H caret, right? And if you plug in here what the same eigenstate of the time independent Schrodinger equation. So what would you get if you act with H operator on its eigenstate? Like by time independent Schrodinger equation, by acting with this total energy operator on eigenstate, you produce eigenstate itself multiplied by a number which is value of energy, right? And then if here it will be also eigenstate conjugated, by using these symbols in between, we remove operator, then we can put the, oh, thank you for helping. And then the like A sub I, which will be energy, will travel outside of the integral. And then in the integral, we will have phi star times phi integrated over whole space, which will be 1 by normalization, right? And then we will have only the eigenvalue, so what you can get on the observation. Make sense?
Yeah.
I'm very happy you just did inspire this question by the style of the presentation. We were not discussing in previous years, so I think we are, as class, we are exceeding what was done before. More questions to Adam? If no, let's thank him once again. So, floor is yours.
All right, my name is Zane Hensel, and I'm doing postulate 5 of quantum mechanics. Definition is the wave function or state function of a system evolves in time according to the time-dependent Schrodinger's equation. And we can tell it's time-dependent by the psi r of t and the psi r of t on the other side as well. I is the imaginary number square root -1. H bar is going to be Planck's constant in, I think it's joules per second. And then H hat is the total energy of the system. The explanation. Postulate 5 in quantum mechanics applies to a particle when the observer wants to know where a particle might be between time 0 and time 1. If the observer wants to know where a particle might be at time 0 only, the observer would want to use postulate 4. This is because in the equation, this is a time-dependent equation. So we will be finding the probability of where a particle might be in a set amount of time rather than at a certain time. And that's about it because everybody else has been building up to this.
Okay, perfect, Zain. By now you are the champion of being most
Yes, sir.
short and
Yes, sir.
Any questions? Anything was not clear, or you wanted to learn more? Any other questions or concerns? 1, 2, 3. Let's thank them once again. And we are going to number 6. Let's see how it will be different from number 5. So next presenter is Pono.
Can you hear me?
Yep. Oh, okay. Nice seeing you. Maybe I'm seeing you for the first time. Welcome to the class.
Thank you. Okay. So I had postulate number 6, which is the time-dependent Schrodinger's equation, and it is a time evolution of a state. So for background, the equation was originally postulated in 1925 and was published in 1926 by Edwin Schrodinger. And then it became the basis of his work going into leading up to winning the Nobel Prize in Physics in 1933. Based on the information I could find, Schrodinger's equation wasn't necessarily derived. It was actually a rework of the equation, total energy equals kinetic energy plus potential energy. And he did this through the use of logical arguments. The Schrodinger equation is a linear partial differential equation that describes the wave function of a quantum mechanical system. So the time-dependent Schrodinger equation is right here. It's just the partial derivative of psi with respect to t, which is equal to 1 over the imaginary number I times h bar times the Hamiltonian and the wave function. H bar is a reduced Planck constant, h over 2 pi, and the Hamiltonian is the sum of the kinetic and potential energy of the system. And this equation demonstrates how a wave function of a system changes over time. And then this equation also assumes that the Hamiltonian is time dependent, which oftentimes is not the case. I can go into full screen. Do that. Okay. Okay. So when H is not time dependent, which is most cases in chemistry, we can summarize the Hamiltonian is equal to the total energy of the system. And then if the wave function is if the H is not time dependent, there are two scenarios depending on if the wave function is an eigenstate of the Hamiltonian. So if the wave function is an eigenstate, you can derive the equation from the equation above for psi with respect to r and t. And then if the wave function is not an eigenstate, the resulting function is this summation at the bottom. And so the impact of the time-dependent Schrodinger equation. So the Schrodinger equation was revolutionary for quantum mechanics and really boosted up the development of the field. It plays the same role as Newton's laws and the conservation of momentum do in classical mechanics. It does that in quantum mechanics. The Schrodinger equation has been used many times to form other equations. For example, the Dirac equation, and it has been used in the quantum field theory. It can be used to describe microscopic and macroscopic systems. So it can describe anything down to subatomic particles all the way up, potentially theoretically scaling up to the universe. The energy frequency relation used by Einstein, Bohr, and Planck can be found in the equation when the H is not time dependent. We can find E over H bar in the exponential, and that is the relationship used for many of their theories. And that's it.
Okay, please, Jeremy, thank you. And please stay with your slides. I want to,
Oh, okay.
or maybe anyone in the class or online has questions. Questions online?
Get back to my PowerPoint.
Just arrow back and you.
Oh yeah, you're right. There you go.
So, two questions.
Yep.
And everyone in the class online or in physically is welcome to contribute. Example of time-dependent Hamiltonian. When your statement will not work. You told almost all in chemistry, but can you project an examples where it is total energy depends on time?
Actually, when I was researching it, every source instantly went to assuming H is not time dependent. So there was very little information on time dependent Schrodinger's equation. They'd cover it and then they would instantly go to time is not time dependent. So I do not have any examples.
Suppose you have a giant capacitor with like plates with positive and negative charge, and you apply electric field there. One side you charge and discharge this capacitor, and in between these plates you do have a polar molecule.
Yeah.
When there is electric field, it rotates towards where it is, right? If you change orientation, it will rotate other direction. But if you change electric field, then the total energy of molecule will change. So oscillating external fields will create time-dependent Hamiltonian. Make sense?
Okay. Yeah.
Can you please go to the next slide? Linguistic question. Any typos in the names of famous people?
Wait, what?
Do you see yourself or anyone in the class see any typos in the last names of famous people?
Bore.
So how should it spell?
I believe it's B-O-R-R, right? No, that's probably not right.
Maybe B-O-H-R would be better.
Yeah, that's right. There we go. Sorry.
Oops. Little typo.
That's fine. That's fine. I wish for the rest of the semester we have only linguistic errors. Okay, more questions to Connor? If no, please join me in thanking him once again. And we do have two more presentations for remaining 11 minutes. So next one is Kennedy. Kennedy, are you on? Yes, you are online. And if your equipment allows, please enable camera so that it's we can communicate better.
Okay. Can you see me?
Yes, yes. Welcome to the class.
Okay.
So two talks will give an overview of mathematical foundations which are critical for solving practical problems. And Kennedy will overview important things on matrices. The floor is yours.
Okay. So I'm going to talk about matrices. So the first one is a matrix by vector rule, so scalar multiplication. And this is very simple to do. Basically, you just take your scalar and then you multiply it to each element in the matrix. So then you get your result. And then matrix addition and subtraction is the same. You can only add or subtract the matrices if they have the same dimensions. So you can take a 2 by 3 matrix added to a 2 by 3 matrix, but you cannot add a 2 by 3 matrix to a 3 by 2 matrix. And then for adding, you just take the first element in your first matrix and you add it to the first element of your second matrix and so on, like I have. And then the product dimension will be the same as the dimensions in your other matrices. So matrix multiplication, you can only multiply matrices if the number of columns in the first matrix is equal to the number of rows in the second matrix. So for example, I have A here, and that's a 2 by 3 matrix, and then I have B, which is a 3 by 1 matrix. And this works because the second number on the first matrix and the first number on the second matrix are the same. So you can do it. If they're not those aren't the same, then you are not able to perform the operation. Also, the first number on the first matrix and the second number on the second matrix make up the dimensions of the final matrix. So to multiply, you take, so in this example, the A times B, you would take 1 times 6, and then you add that to 4 times -1, and then you take -2 times 3, and then you just add all those together, and then that will give you your upper product in the matrix. And then you take 3 by 6, you add that to 5 times -1, and then you add that to 2 times 3. Add all those together, and then that will give you your bottom part of the matrix for the final product. And for the determinant of a matrix, basically the way I learned how to do this is what I do is I would like circle the A in column 1 in row 1. I'd circle that, and then I'd cross out the rest of the column in that one, and then I'd cross out all the rest of the row in that one. So then you'd be left with the A11, and then you're left with the A22, A23, A32, and A33, if that makes sense. So this is what's left after you cross out the column and the row, and then do the same thing. And then once you have that, you take the A11, and then you multiply that by basically the diagonals. So you take A22 multiplied by A33, and then you subtract that from A32 times A23. And here's an example of that. So you take the 2, and then you take 0 times 5, which is 0, and then you take 4 times -1, which is -4, and then you subtract those together, and you get 4. And then you're going to add the 3, and then you times 2 by 5, which is 10, added to -1, or added to +1, sorry. And then for the last one, you do 2 times 4, which is 8, plus -0, which is 8, and then you add all that together and get 49. Then the inverse of a matrix, you just use this formula. You take your original matrix and you inverse it, which would be 1 over A times D minus B times C, and then you take that times the matrix of A and D flip-flopped from the original one, and then you add a minus sign to C and B. And then here's an example of that. And that's it.
Okay, please join me in thanking Kennedy. Any questions?
For inverses, do they just work on 2 by 2 matrices, or do they work on all square matrices?
I believe they work on all.
Yep, yeah, I agree. And the formula is different for each one. It's a little bit weird for each one. They're all geometric crap. So,
yeah.
But yeah, I agree. Mm-hmm.
Okay. I do have a brief question, but let's probably postpone it to the next meeting because we are short in time. I'll ask, but if there is no immediate answer, we'll discuss later. How do we? What is the best use of the determinant? Where can we practically use it? And if there is no immediate answer, just let's postpone it because it's like an extra question. Like, what is practical use of determinant for science and engineering? Let's deposit this question because we can discuss it longer. And if there are no more questions, let's thank Kennedy once again. And last but not least is August M. So please share screen and enable camera if possible. Okay, I see you. And August will continue a bit more on matrices, and then overview once again most important postulate that we consider today. So floor is yours. Please go ahead.
All right, thank you very much. So today we'll be talking about diagonalization of matrices, eigenvalues, and eigenvectors, as well as postulate 6, just sort of an overview of postulate 6 once again, since it is a very important postulate that we're going to be going through 3 times. So, all right, so postulate 6 overview.
And last but not least is August M. So please share screen and enable camera if possible. Okay, I see you. And August will continue a bit more on matrices, and then overview once again most important postulate that we consider today. So floor is yours. Please go ahead.
All right, thank you very much. So today we'll be talking about diagonalization of matrices, eigenvalues, and eigenvectors, as well as postulate 6, just sort of an overview of postulate 6 once again, since it is a very important postulate that we're going to be going through 3 times. So, all right, so postulate 6 overview. This will just be a brief touch on time-dependent wave functions. Postulate 6 is defined as the time-dependent Schrödinger equation. Yeah, I know I pronounce Schrödinger weird, but it's I h bar del psi over del t is equal to the Hamiltonian operator of psi. So the Hamiltonian operator gives you an eigenvalue of energy for your psi operator, or psi eigenfunction, and the energy is directly related to del psi over del t, which has various implications that will be explored in the next slide. And this is only available for like imagining a simply derivable or differentiable wave function. There are different types of wave functions that you can use. This is just the most simple one that is used in this case, and this is what gives the postulate. It is simply a complex exponential that yields this relation, and it only works for certain exponentials, but it does not work for certain other exponentials. Thus, it needs to become a postulate. Since t is the only time-dependent term, the derivative just becomes negative I over h hat, or h bar e of psi is equal to the partial with respect to t of psi. So fairly easy differentiation. So importance of postulate 6 is that it's very useful for interpretations of wave functions and quantum mechanical systems. It predicts wave functions can form stationary waves or standing waves. And it shows how the wave function changes with respect to time and how that leads to the energy of the wave function if you dig a bit deeper into the equation. Although one problem with it is that it assumes an analytical solution to the time-dependent Schrödinger equation, which unfortunately sometimes there isn't an analytical solution depending on the wave function that you have. It's only true for simple 2-body or 1-body systems. Additionally, it's really only effective for slow-moving particles and systems because it's a non-relativistic equation. If you want to use it for fermions or electrons, basically, you want to use the Dirac equation. But otherwise, it's kind of useless when representing highly relativistic speed systems. as well as plugging in parameters for hydrogen atom gives ground state orbitals, and used with some hacks for computation, such as, Hartree-Fock approximation, etc. All right, now onto matrix diagonalization, eigenvalues and eigenvectors. Basically, diagonalization, what it does is it takes a square matrix and converts it to a diagonal matrix. This only works for square matrices. It does not work for any other type of matrix. This is frequently used in physics, as this gives the eigen vectors, which you can get the eigenstates from, and it gives a diagonalized matrix, which has very special properties that accommodates for the original matrix that is non-diagonalized. So basically what it is doing is it transforms the underlying matrix system of equations into coordinate axes. Basically, it's aligning the linear system equation to coordinate axes that stay linear during transformations. So as shown below, this is the eigendecomposition equation. And essentially all it is a matrix A, which is non-diagonalized, is equal to the matrix corresponding to the eigenvectors of A times a diagonalized matrix times the inverse of your matrix corresponding to the eigenvectors of A. All right. And now we're talking about eigenvectors and eigenvalues. Eigenvectors are characteristic vectors given by the linear transformation of the system of equations encompassed by a matrix. So we all know that we can describe a matrix as a system of equations. These vectors are put under a constant scale when put under these linear transformations. These vectors only change by constant when the set of linear transformations of a certain matrix is applied. And eigenvectors are essentially always orthogonal to each other if they are different vectors. If they're the same vector, obviously they're the same, but if they're different, they're always orthogonal. And that's very useful for integration, particularly. As for eigenvalues, the constant eigenvectors change by, it's basically the constant the eigenvectors change by under a linear transformation of a certain matrix. Physics terms are a little bit more broad with the use of eigenvectors and eigenvalues. For instance, using the very, very basic equation for the Hamiltonian. H is just a Hamiltonian operator. When plugging in an eigenfunction into an operator, it equates to some eigenvalue multiplied by the eigenfunction. In this case, the eigenvalue is energy, and the wave function is the eigenfunction. And I believe that is all that I have.
Okay, let's join me in thanking August. Any questions in class or online? If you do have any questions, you can deposit an email because we are a little over time. I don't have major questions as well. Let's thank August once again, all speakers. Those who are online can see the class. If I enable camera, so you can wave hands to your online classmates. And everyone who presented today get an A for the first midterm exam. So you're progressing well towards completion of the course. You worked hard. Therefore, there is no homework for this weekend. Have a nice weekend. See you on Monday.